Okay, let's just dive right into this. We're doing a rapid-fire explainer today, literally compressing years of mathematical logic into a massive 5-minute visual sprint. If you're looking to truly grasp the core of IGCSE Mathematics B, you are in exactly the right place. We're going to connect all the dots across the entire syllabus. Now, you might be thinking, master it in 5 minutes? No way! But here's the thing, math isn't just some random assortment of rules you have to memorize. It's a universal toolkit for solving real-world problems. Today, we aren't just memorizing formulas. We're looking at how numbers actually define the universe around us, whether that's the trajectory of a thrown stone or the massive orbit of a spacecraft. So, here's our roadmap for the explainer. We're going to build your ultimate problem-solving framework across 5 major pillars. 1. Algebra and core tools. 2. Graphs and real-world kinematics. 3. Geometry, mensuration, and trig. 4. Vectors, matrices, and transformations. And finally, 5. Sets, probability, and statistics. Let's hit it! Starting off with Pillar 1, Algebra and core tools. This is the absolute bedrock of everything else we're going to cover. At the foundation, we have linear equations and their cousins, simultaneous equations. These are what allow us to find unknown values by perfectly balancing both sides of a scenario. When you look at an equation like 4x plus 15 equals 20, you're literally looking at a perfectly balanced scale. Once you learn to manipulate one variable, or even two at the same time, you've totally unlocked the ability to solve for the unknown in pretty much any basic mathematical model. And to manipulate these variables efficiently, well, we rely on the rules of indices. Think of these as vital shortcuts for simplifying massive numbers in fractional powers before you even start calculating. Multiplying values with the same base, just add the powers. Dividing, subtract them. A power raised to a power, multiply them together. These aren't just neat tricks. They are absolutely crucial rules that keep algebraic expressions manageable, especially when things get messy with complex roots or standard form. Now, understanding how these variables relate to each other is a huge deal. You have to notice whether they scale up together in direct proportion or if they work inversely, like if one value goes up and the other drops. Say you increase your speed, so your travel time decreases. That's inverse proportion. Grasping this algebraically is literally what lets us model real physical rates of change. Okay, moving right along to Pillar 2, Graphs and real-world kinematics. Let's take those abstract numbers and give them some shape. See, equations aren't just floating numbers. They map physical reality. Take the classic example of predicting the exact trajectory and maximum height of a stone tossed off a cliff. In our model here, we see the height, h, tracked against time, t. And because we have that negative t-squared term, we know algebraically for sure that this stone is going to rise to a peak and then accelerate downward toward the sea. And what's really cool is how we translate that algebraic formula into a table of discrete data points to form a smooth curve on a graph. Just by substituting time values into our equation, we plot the exact journey. 0 seconds, it's 30 meters high. 3 seconds, it hits 42 meters. Graphing this lets us visually pinpoint the exact window of time when the stone is, say, hovering more than 40 meters above the sea. We even use these exact same tools for physical optimization. It's like applying step-by-step calculus to design a swimming pool with the absolute maximum volume, given a really strict surface area limit of 200 square meters. You form a volume equation, calculate the derivative, setting dv over dx to 0, and boom, you find the exact mathematical turning point. It's so satisfying to see the abstract world of calculus solve very tangible, real-world engineering constraints.
All right, on to Pillar 3, Geometry, Mensuration, and Trig. We're applying that logic directly to physical dimensions now.
The math you're learning here actually operates on a cosmic scale. I mean, it's capable of calculating that a spacecraft orbiting the Earth 58,376 times travels a staggering 2.656 billion kilometers. By just understanding the circumference of a circle, you can take that massive distance, divided by the number of orbits, and instantly figure out the exact radius of the spacecraft's orbit in space. Mind-blowing, right? But to really navigate geometric space, you need concrete rules, like the intersecting chord theorem. This acts like a super reliable compass for finding unknown lengths and angles within circles. If two straight lines intersect inside a circle, the product of their segments is perfectly equal. PE times PC will always equal PB times PD. These symmetrical properties of circles are just absolute and unwavering. That brings us to Pillar 4, Vectors, Matrices, and Transformations.
how do we systematically manipulate all that space?
Well, matrices are basically just structured numerical ways of commanding a shape to reflect, rotate, enlarge, or translate across a coordinate grid. Whether you're sliding a triangle across a plane using a column vector or flipping it across the y-axis, matrices are handing us the precise mathematical instructions to map an original object exactly onto its new image.
And to actually measure those movements, we look at vector magnitude. This combines vertical and horizontal shifts to calculate the exact absolute distance of our movement. By representing a vector as a directed line segment, we're basically just using Pythagoras' theorem, the square root of x squared plus y squared, to find the actual physical distance that vector covers. It's really that simple.
And finally, Pillar 5, Sets, Probability, and Statistics. Let's see how this builds our ability to predict the unpredictable.
Before we can even begin to analyze probability, we have to group our data into sets. We use Venn diagrams to clearly define the overlap between different groups, like say, students taking both physics and geography. By rigorously defining our universal set and tracking exactly where elements intersect or complement each other, we bring absolute logical order to totally chaotic, raw data. Once we've done that, visualizing simple and combined probabilities becomes a breeze. And it proves that the chance of all possible events always mathematically adds up to exactly 1. So if the probability of drawing a white ball is 0.9 and a black ball is 0.04, well, the probability of picking neither is simply 1 minus those chances, leaving us with exactly 0.06. Math leaves literally no room for unaccounted possibilities. Then, we apply these statistical odds to the real world. Think about calculating the exact expected frequency of rejecting batches of faulty calculators on an assembly line. By using relative frequency in tree diagrams, we scale up simple probability, like drawing a single faulty unit, to predict exactly how many batches out of 1,000 are going to be rejected in a factory over a whole month. Real game-changer stuff.
But to draw true inferences from all that data, we have to carefully distinguish which statistical measure to use. We constantly compare the mean against the median, depending entirely on the spread of our information. If you've got wild, extreme outliers in your data, the median, the literal middle value, is often going to paint a much more accurate picture of reality than the calculated mean ever could.
So there you have it. You've just sprinted through the logic, space, and statistics of IGCSE Math B. But honestly, the real question now is, which real-world problem are you going to decode using this mathematical toolkit? We've seen how algebra models physics, how calculus maximizes volume, and how probability predicts mass manufacturing. The math you've seen today isn't just some curriculum you have to get through. It's literally the source code for understanding reality. Thank you so much for joining me on this explainer, and hey, keep exploring out there.